In the last few videos, we have created a general structure for the simple auction contract. We have added some variables, some functions, but what is still missing is the general logic. So it's obviously not a working auction contract yet. But that's going to change in this video. In this video, we are adding the logic, we're having some restrictions, additional functions, and we'll make sure that our smart contract can actually accept if. All right, let's go. So the first thing we're going to add is some conditions, some end conditions. So basically we're saying at some point our auction contract must conclude. At some point we have to determine a winner of the auction. And you can do that in different forms, but usually the way it's done is through a specific point in time when the contract ends, when the auction ends, and that's exactly what we are going to do. But this also leads to the question of how a smart contract keeps track of time. And it's not that straightforward when you think about it, because essentially we're talking about a distributed network. We are talking about a blockchain network with multiple nodes, with a large number of nodes. And of course, in this case, when it's decentralized, when it's distributed, these nodes may have a slightly different understanding of time. Okay? So again, this leads to the question of how do we implement a timing condition like that? And the way we do that is Solidity offers some global variables, and what we can do is just use block.timestamp. This gives you the time that the miner has set for a specific block. So when a miner comes up with a solution, with a valid solution, when they propagate this block and it gets accepted by everyone else, then within this block there is also this timestamp variable that is set by the miner, and that's what we can use to conclude our contract. Now, you have to be aware that, of course, the miner has some room for variation in there. So even though there are certain rules, the timestamp that is set by the miner must adhere to, this can still be influenced by the miner. So there is some variation. The miner has some possibilities of influencing that specific variable when they are creating the block. So for security reasons, I mean, you should not use that for actual funds on mainnet. That's not a good idea, because essentially the miner can influence, at least partly influence, the execution of the contract. In that case, you might be better off using something like, for example, the block number. When you know that on average, let's say every 13 seconds a new block will be created, then you could just compute how many blocks it will take on average to reach a certain point in time, and just basically define your time condition as a block number instead of this timestamp, and that's somewhat more secure. It also has its issues, especially because it's of course an average value, but that's something you could do as an alternative. Here we go with the easiest example. We just go with the block.timestamp that gives you the variable that has been set by the miner. And that's perfectly sufficient for our proof of concept use case, but again, don't use it for actual funds on mainnet. You might run into some problems there. There are other block variables, of course, for example, block.baseFee that returns the base fee of the current block. Block.chainID returns basically the rules under which this block has been created. Recall, the chain ID refers to a specific instance of the blockchain. So we have a chain ID for mainnet, we have a chain ID for all the various test nets. There is a chain ID also for Ethereum Classic as an example. And of course you have a chain ID when you're creating, when you're setting up your own blockchain, for example, using Ganache, basically a local test blockchain, and also it has its own chain ID. Then you have the block.coinbase that returns the miner address of the current block. So basically the address of the person who has created, who has successfully assembled and propagated the most recent, or not just the most recent, actually this specific block where the transaction is included. Then you have block.difficulty that returns the current block difficulty with regards to proof of work. You have block.gas limit returns the block's gas limit, and block.number returns the block's number. And as always, this refers to the block which whether the transaction, so the specific transaction that uses these block variables is contained in. Okay, if you are looking for additional variables, global variables, go to the Solidity documentation. As always, It's a good idea to look into the Solidity documentation because it's, first of all, it's really well written. Second, much of what we're doing here is actually based on the Solidity documentation. So whenever you have additional questions, you should go back to the Solidity documentation and see if there is additional information in there. So let us look at some other useful global variables, some of them which are really frequently used. For example, message, msg.sender, so message sender. It's the sender address of the message, which means it's the sender address of the current call or the current internal transaction. This is not necessarily the origin of the transaction. We will see a global variable that actually uses the origin. But let me give you an example. When you have an externally owned account that initiates a transaction, and then this transaction is a contract interaction. So it invokes a function in a specific contract. But then this contract, as part of the function execution, invokes a function in yet another contract, for example. Then in this last internal transaction, there would be a difference between message sender and what you will see later on. We have it actually, or where is it? Right here, transaction origin. Transaction origin always uses the EOA that has initiated the transaction. So you get the original sender address from the transaction. And with message sender, it's the most recent call. So you basically just go back one step and you take the address from whatever account, so externally owned account or contract account for that matter, has invoked the last function call. And you get that address back. Okay, so there's a difference. And for many applications, message sender is much more secure because when you go with the transaction origin, this may lead to issues because essentially you cannot check for what has been done in between. And if you're checking just the transaction origin condition, then some smart contract could actually do something on behalf of the original sender, which would be a really bad idea. So in most cases, you should just go with message sender, and that's probably the better idea for your applications. Message value is the ether amount in way sent with the message, so sent alongside the message as part of the message. And then you have others like message data, that's the complete call data. Then you have message sig, that's the first 4 bytes of the call data. That indicates basically what function has been called. That's the function signature. Then you have the transaction origin. We just talked about that, which is closely related to message sender, but gives you back a different address, gives you back the original address. In many cases, it gives you back a different address. It doesn't have to be always the case, of course, when you have a really simple call that is just one step. And then you have a transaction gas price. It's the gas price of this transaction, the gas price that has been set as part of this transaction. You have block hash for a specific block number that indicates or gives you back the hash of the specific block. Okay. Again, use the Solidity documentation as a quick reference guide, basically as a cheat sheet for your reference. Then, of course, Solidity also supports time and monetary units. It does so natively, and I think that's quite an advantage. So, for example, you could go when you're defining, let's say, UINT, it's called amount. Then you could just say it's 1 ether, and it's just much more convenient instead of typing a 1 followed by 18 zeros. So you just have this additional keyword right here, ether. And if you assert, so basically you make sure in your code that something holds, and something that should always hold, then you have amount right here, the amount you have defined equals 1 to the power of 18. And again, this will pass. So the most common keywords are way 10 to the power of 9, and ether 10 to the power of 18. Time suffixes can also be used. For example, what you can do right here is you have UINT, 2 hours, so that's the variable. You set it to 2 with the keyword hours, and then you can again assert that it's the same as 2 times 60 times 60. And you can see by that example that it will always be converted to seconds, so time essentially is stored in second values. Okay? And the keywords we can use is seconds, minutes, hours, days, and weeks. So what's important to understand is one thing you can't do, that you should not do, is the example right here on line 2. When you're saying you have a UINT with the name 2 hours, and you're just defining it as number of hours as defined up here, hours, that is not allowed. So you could use the 2 directly, of course, here, but as soon as you have a variable here, then you want to follow it up with a keyword, then you need an additional step, and it's quite easy. You just have this times symbol, so this little asterisk right here, 1 and then hours. Okay, so you cannot just use the keyword directly, just make it times 1 and then the keyword, and then it will work just fine. This right here will not work, so that's something you have to keep in mind, and that will help you because it's somewhat not intuitive that this might be an issue, and you might run into that when you're coding your own contracts. So that's why we are telling you specifically. All right, so let's add the duration to the smart contract first. So basically how long it's going to run. And of course, we're also doing that as part of the constructor. So the first thing we're doing right here is, you can see the end time, of course, public end time. And we're setting that as part of the constructor. So you have the parameter in the constructor, which is called duration minutes. Okay. So you have the UINT, duration minutes. And then as part of the constructor, you're not only setting the beneficiary as we did before, in accordance with the parameter, you're also taking the duration minutes that has been set as part, that's been chosen as a parameter in the process of deployment. And then you're setting end time equals to block timestamp, so the current one, plus duration in minutes times minutes. So you're doing that because we have said that initially it gets set in minutes right here. Duration in minutes obviously prompts the user to set it in minutes. So you have to make sure that this parameter right here is also used in minutes. If you wouldn't do that, it would be in seconds. That wouldn't be a good idea, okay? So basically as part of the constructor, you're setting the end time, and you want some flexibility that the user can actually choose that end time. So just as we did with the beneficiary as part of the constructor, you're also doing that with underscore duration minutes, which then gets assigned to the end time variable. All right. So in many cases, functions in the contract must be restricted. And I already told you that you could create your own custom modifiers for that. In many cases, however, people will not do that because they think it's much easier readable if they explicitly code it every single time it's used. But one candidate for such a function where we need some restrictions certainly is the bid variable. In particular, bid should only be callable during an active auction. Once the auction has ended, you should not be able, and no one for that matter should be able to use the bid function anymore. Okay, so Solidity offers the require keyword. So you're saying require followed by a condition with a comma right here, and then you have an error message. Okay, so you basically add the condition, whatever you want to check. And in case it goes wrong, that is the error message that gets shown. What's important to understand, this will also be really important later on in the when we're looking at DeFi, in particular when we're looking at flash loans. This is a concept you must understand in case something goes wrong. So when the condition evaluates to false, the whole transaction will be reworded. It still gets included, it still gets added to the blockchain, but it will not lead to any state changes except for the update of the nonce, and of course the transaction fees that get deducted from the account that initiated the transaction. But any of the executions that have been part of the transaction itself will be reworded and will not lead to state changes, even though the transaction gets included to the blockchain. And as I said, you can add an error message. It's optional, but I highly encourage you to do so. It's just much easier to play around with these functions later on when you get an error message in case something goes wrong, okay? So let's restrict the bit function. Here we have the bit function. So bit, it's a public function, and we simply require that the block.timestamp must be smaller than the end time, and the error message is auction ended. Okay, so basically indicating that you cannot use the bit function anymore because the auction has already reached its end time, so it concluded already. So now we have to accept and store valid bits, because of course it's great when you have the restriction and when you have a specific end time, but we need some way of storing the bits. We need some way for the contract to accept actually ETH, and this is part one of the logic that we need for our auction. So the first thing we do is we add the payable modifier to be able to receive Ether. We do that right here as part of the function. So you're not just saying it's public, you're also saying it's payable, and that indicates that when somebody interacts with the function, when somebody invokes the function, that they can send some ETH along and that the contract will actually accept that ETH. Okay, but that's what you're doing with the payable modifier. All Ether received are in full control of the contract, so they are basically locked on the contract, and that's also a concept that will become extremely important later on when we start talking DeFi protocols. Whenever you have a decentralized finance protocol, always, I cannot think of a single example where there aren't any assets stored on the smart contract itself. The usual idea is that you have this contract, the contract has certain conditions, it takes custody of some assets, and the assets can only be released if certain conditions are met, okay? And that's something similar right here in the auction contract. We are also storing assets, in this case Ether, on the contract, and these assets which are stored on the contract through these bits are subject to the rules of the contract, can only be released later on under certain conditions, and only of course to specific addresses. So the first thing we do is we check if the bit message value is higher than the previous valid bit. So we have that right here, require that message value is larger than the highest bit. So the currently highest bit, the current highest bit. Otherwise we say bit too small. That's again the error message. And if that is successful, so if the auction is still active, we did that before, right, where we check the timestamp and compare it to the end time. And also if the message value is sufficiently large, then we're doing two things. First of all, we're storing the message value in the highest bit variable of the smart contract. And the second thing is we're storing the message.sender in the highest bidder variable of the smart contract, okay? So that's great, but we could also end up in a situation where we have competing bits. So you could have one account, let's say account 1, who is bidding. We will make such an example later on, let's say 0.1 ETH. And then before the auction concludes, we have somebody else, let's say account 2, who will bid 0.2 ETH. And in that case, of course, the second account with the 0.2 ETH will be the highest bidder and the highest bid. Account 1 is not in there anymore. I mean, and of course, in that case, we need some way of refunding account 1, because it wouldn't be a good idea when just every single one who placed a bid, even if they do not win, wouldn't have access to their funds anymore. So obviously, the outbid must be refunded. The bid amounts that are not the highest bid must be refunded to their respective sender addresses, okay? So remember that a smart contract is unable to initiate transactions by itself. We said that, I think, actually in the first video, and that's something where there are a lot of misconceptions where people think that a smart contract can just initiate something. But again, transactions always have to start with an EOA, so the externally owned account has to initiate these transactions, and then smart contracts can only respond when they are invoked, when some of their functions are called, okay? So we have two options essentially. Number one, we could set the refund as part of the new bid transaction. So we say whenever there is a successful new bid, then we could just refund the old old or the previous highest bid to the address who did that bid specifically. Okay, that would be option one. And option two would be to allow the user to withdraw his invalidated bids. So basically say, okay, it remains on the contract, the ether, but the user who has been outbidden can withdraw his or her funds later on. And we actually will go with the second option, that's our preferred option in this case, for two simple reasons. First of all, it can in some cases make the execution more costly when you make it part of every single transaction, as proposed in option one. And second, passing the execution to another address just introduces a significant and unnecessary security risk. It's just much cleaner when we say the person who actually placed the bid is the only person who can withdraw the bid, and that's what we're going with. Okay, so we will exclude that. We will have a different function, a separate function, a withdraw function, where the user who has been outbidden can withdraw these funds later on. All right, so of course we have to keep track of how much ether a previous bidder can withdraw. So we have to store that somewhere, and we use a mapping for that. Okay, so we say mapping, store key, and then a value. So it's this key value pair as always. And as explained already when we talked about variables, it's quite similar to a hash map. You can think of it that the position on this storage array we talked about is determined by the mapping variable itself, so by the position of the mapping, but then also, of course, by the key, and essentially it's just the hash value of the two. So the way you declare it is you're saying it's a mapping, you have the key type, and then this little arrow symbol right here, which is just an equal and a greater than sign, and you assign it to a value type. You have the visibility, we will set it to public later on, then the variable name. Okay. Now, as always, when you are declaring it as public, then of course Solidity in the background will create one of these getter functions, and that's also what we're going to see here. With the getter function, you have to provide the key, and then you will get the value type. Okay. So you will get back the value in this case. In our case, what you would do is you add the address, and you can see how much ether this address can still withdraw. So let's implement that really quick. The first thing we have to do is adding this mapping up here. So you have this comment, allowed withdrawals of previous bits. We create this mapping from an address through to a UINT. And we declare this as public to get the getter function. We can easily look at how much each address can still withdraw, and then we call that pending returns. In the bid function, we also have to slightly adapt that. So this stays the same, the required condition. This also stays the same. But then we say if highest bid isn't 0, then we set the pending returns of the highest bidder. So that's the address right here, set to the highest bid. But we don't just do that with an equal, we do it with a plus equal, and we do that in case there has already been something in the pending returns for that address, that we do not override it, but rather add to it. So imagine a situation where a specific address has already bid a certain amount, then has been outbidden, then bids again a higher amount, and is outbidden again. Of course, in that case, you don't just want to take the second bid of the outbidden bidder. You want to add the two so that the person can withdraw all of his or her previous bids that have been outbidden. Okay, that's the idea. And then again, here you set highest bid to message value and highest bidder to message sender. That remains unchanged. So basically what you're doing is you're adding right here the pending returns, and also of course you have to define that pending returns mapping. You have to declare that in the initial statement. In many cases, these mappings are super powerful, but as always, things, of course, have their drawbacks, and that's not any different from mappings. So with mappings, and we have already briefly talked about that in one of the previous videos where we talked about variables, they have no length property, so you cannot just ask how many of these keys lead to non-zero values or have non-zero values assigned. So you cannot get back the length from a mapping. It cannot be enumerated or returned. You always have to ask for specific keys to get a certain value. And also these mappings cannot be cleared easily when you want to say you want to set back everything to zero, let's say. So there is no straightforward way to reconstruct storage state, but what you can do, and this is done in many cases, you can separately store all keys that have been used, and that's a workaround in that case. When you store these keys in a different variable, then you basically have a list of what has been used in the course in your contract, and if you want to change them later on, or if you want to have a complete list, then you just refer to all of these keys. So that's something you can do, but when you're just operating with the mapping itself, then there is no such list, and the only thing you can do is ask for a specific key and get the value for that one. But you also have to know, we didn't use that here, but mappings can be nested. For example, you could say, okay, I have a mapping with the key address, and there again I have another mapping where there are multiple entries for that address. So I'm using a UINT, and then I check for a Boolean value, for example, and this just means that there are multiple entries for one address, multiple true and false values, okay? So the next thing we're going to do is we have to explicitly create a withdraw function. I mean, it's great when we know that somebody still has some money in custody of the smart contract and that they should be able to withdraw it, but without an explicit withdraw function, they simply cannot do that, right? So that's the next step we're going with. And for security reasons, Solidity differentiates between payable and non-payable addresses. So if you want to be able to send Ether to an address, then it must be explicitly declared as payable. I give an example right here. You say address with the payable modifier, and then you have a payable address, and you can just use that to send money to. Okay, if you haven't declared it as payable, then your contract will not be able to send money to that address. So there are various ways in which we can send the Ether. Number one is we could say transfer, so then the amount. This forwards exactly 2,300 gas and tries to transfer the amount that has been specified to the target address. And what's important to understand is that when the transfer fails, then it will revert the entire transaction. The second thing you can do is you can use send. With send, you also have the amount right here, and it also will try to transfer, or rather send in this case, the amount. But the difference to the transfer is that it will not revert on failure. So it just returns true or false. You can work with that, but it will not revert the entire transaction when it fails to do so. And then you have a call. With call, that's a low-level call to the address. It forwards all the remaining gas or an exact value when you specify that. I mean, what you have to do if you want to add some Ether to that, you also have to declare not just the gas, as I said, gas amount, but you have to declare some value, so a value amount, and that's how you specify how much Ether you want to send as part of the call option. Now, for simplicity and security reason, we are using transfer. So we're going with the first option right here. But this also means that you're basically just sending the Ether, and you cannot do anything else with it because it will run out of gas, right? I mean, you have just these 2,300 gas which are needed to send the ETH. And if you want to have forward compatibility, so if you want to be in a situation where you can, let's say, do something else when you're transferring the money, when it's going to a small contract, for example, and if you want to be forward compatible, then there are good reasons to use call instead. In this case, we don't need that. In this case, we're simply going with transfer. It's perfectly sufficient for our case. All right, so let's implement this withdraw function. So we're saying, okay, function withdraw, we're setting it as an external function. This shouldn't be able to be used by the smart contract itself. There is no reason for that. It will always be an external account who is doing that. It will return something, so you have the return statement. What will it return? It will return the UINT amount, okay? That's basically what we get back. We set amount equal to pending returns for the message sender. So that's looking in the mapping for the pending returns for the value using the message sender address as the key. And then we're saying if the amount is greater than 0, then we send the pending returns of the message sender to 0. And we make this address right here payable and transfer the amount that has been defined right here to the message sender, okay? Optionally, you could have an explicit return statement right here. That's not necessary when you're declaring it in that way. When you're just saying returns UINT amount, then you will get back the amount as a return statement anyways. But they're all different philosophies. Some people like to explicitly code that return statement, but you can just simply do it that way. Now, what's super important, and we will also talk about that later on when we look at the structure and how you have to structure smart contracts, is that you update everything that's internal to the contract, so any state variables, before you transfer the amount. So before you interact with an external an account. And that's just important because otherwise somebody could create a smart contract in a way that just re-enters your contract and basically in this case drains your funds. So it's always good to just update the variables in the contract first before you're transferring anything or before you're interacting with anything external for that matter. That's just something you have to be aware of. It's some really basic way of defending against one of the most common attack vectors with smart contracts. So it's just something you should strictly stick to and make sure that you always update the internal states first before you're interacting with anything external. So then, of course, we also need a function that allows us to end the auction. So after end time, the highest bid should be transferred to the beneficiary, right? So it's actually somewhat of a clean-up job. Of course, when the end condition is met, nobody can bid anymore. But one thing we still have to do is officially end it, and by officially ending it, sending the amount, so the highest bid, to the beneficiary of the auction contract. And again, I know we already talked about that several times, but I get never tired of saying that again. Recall that smart contracts cannot do anything by themselves. So again, we need this function. Again, we need to be triggered by somebody from the outside, by an EOA initially. So we have the auctionEnd function, and we create that in a way that it allows people to close the auction and transfer the bid if needed. What we're doing when we're structuring it, and that's again to prevent certain attacks from occurring, is we first check all the conditions. Second, we apply all internal state changes, and then first we interact with other addresses. And that's the auctionEnd function right here. So we set it as an external function again, because there's no reason why the contract itself should be able to interact with it. Here you have the check all conditions part, here you have the apply the state changes part, and here you have the interact with other addresses part. So basically what we do first is we require that the auction has not been ended before. If it already has been ended, then there is no reason to call it again, and we throw the error message auction has already been ended. Then we require that the block timestamp is larger or equal to end time, and if that is not the case, then we say wait for auction to end. So you cannot end it when the end time has not been reached yet. Then we apply all internal state changes. What you do is you say has ended will be set to true. Okay, so basically what we have checked right here and said this, if this has already happened, then somebody already called a function. That's the reason for that, because here we're setting it to true. And then third, we declare the beneficiary address that has been stored as part of the constructor, as part of deployment, as payable. and transfer the highest bit to the beneficiary. Okay, so the beneficiary gets this amount, the beneficiary gets sent the highest bit as part of this cleanup job, as part of the auctionEnd function. All right, there is one last thing we have to look at, and that's events. And as you will see, events essentially are the locks of the blockchain. But let's start with a motivating question. We already are aware that the blockchain is fully transparent, and we are aware that even if in cases where there is no explicit getter function, people can still get out the value. They cannot use it in the execution context. They cannot use it as part of a transaction when there is no getter function. But if they are just interested in the value itself, let's say for research purposes, they can just look in the storage. And there is a way to get it out. But does this mean that one can just obtain the full history of bits? And the answer to that is yes. Although it's using a lot of resources, because what you would need to do that is access to a so-called archive node. And the archive node essentially allows you to call the state at every block level and to check for the bit variable at a given point in time and for a specific block, okay? So wouldn't it be easier if we would just store the bit of each user permanently on the blockchain? So that we can easily refer to that we have, let's say, a list where you can see the historic development of these bits and basically the sequence of all bits. And the answer to that is no, because this would be extremely expensive and it could cause so-called state bloat. If you don't need it, then you shouldn't store it in that way on the blockchain. There is a much better solution to that, and this solution is events and writing logs, essentially. Why? First of all, it's much cheaper because it's stored in a different place than the state. It's still verifiable. It's part of the block hash, so you could make the argument that it's part of the blockchain, but it has the downside. But if used correctly in a correct way, it's not particularly a downside, because that's exactly what it's for, that it cannot be accessed as part of the transaction. So it's this additional information. It's basically you saying we need these events to snapshot certain things that have happened, to give the users the information, to give anyone who's interested in contract the information of what has happened. And you also have the additional upside that, for example, front ends can subscribe to these events, can listen for these events, and when these events get emitted, then they can respond to it, for example, by refreshing the front end, okay? So how are these events declared? Essentially what you're doing is you declare it by the keyword event, you give the event a name, and then you can have multiple parameters. They are structured in the way parameter type. You're saying whether it's indexed or not, and each parameter also, of course, needs a specific name, and here you could have additional parameters. Once emitted, the corresponding log can be queried from a full node, so you can ask for it. You can ask for all the events of a specific contract, and as I said, you can also subscribe to them and basically listen for the events, listen if something has happened. Indexing is slightly more expensive to emit, obviously, but an index parameter can be used to filter these logs, so you can ask for a specific value for a parameter that has been indexed. And there is a maximum of 3 index parameters per log, so you cannot use the index keyword for any more than these 3 parameters. To emit it, the event, so that's the declaration up here. If you want to emit it, you basically say emit, event name, and then you have the values here in the brackets. And that's how you emit the event as part of a function. And right here, I already mentioned that several times. I think that's really important to understand, is that most node clients offer functionality to subscribe to events and to get notified whenever something happens. So whenever a specific contract emits a specific event, then this just allows you to update the wallets, to update the front ends, to update any of the infrastructure that's interacting with the blockchain. That is usually done through these events. So when we are building these events, then we first add here an event section. So you have to comment events, then you're declaring the events, event new bit. You're saying, okay, we have an address. We want it to be indexed so that we can ask for specific addresses. We call it bidder. And then we have the second parameter, which is an unsigned integer, and we call that amount. And then we declare a second event. which is called auction ended. We have an address, a winner address, and we have a UINT, an amount, so basically the winner amount, okay? So that's the way you declare these events, and then to emit them, you just add them to the respective function. So in this case, we have the bit function where you have to where you emit the new bit event. And in terms of the parameters, you're saying, okay, this first one is the message sender, and the second one is message value. So obviously the address should be the message sender, the person who bits, and here the amount, that is the message value. You know the amount that has been bid, okay? And then the second event gets emitted right here as part of the auction end function. So you're saying emit auction ended event, and the two parameters are highest bidder and highest bid, so that you know how the auction actually concluded, who has won, and what this person has paid. Now, let's actually combine all of these things. I've shown you all of these code snippets, I've shown you different concepts, but now as part of exercise 1, it's your job to first add the code snippets shown in the slide deck to the simple auction contract. So basically to extend the contract we have written previously by these different parts, and then second, deploy the contract, the simple auction contract, and interact with it using different addresses for bits, for example, to end the auction and just to interact with it. All right, so let's go. The first thing we're going to do is we add an additional state variable. It's an unsigned integer, a public one, and we call it end time. And end time essentially is the Unix timestamp at which the auction will conclude. We add it to the constructor first as an argument, so as an unsigned integer underscore duration minutes to indicate that we expect the user to enter the number in minutes. Then in the body we set end time equal to block timestamp plus duration minutes times 1 minute, so to make sure that there will be a conversion to seconds later on, that the user can actually add it in minutes. And then with that we can add our bit function. So with the bit function, that's a public one, we first check two requirements. So the first requirement, we check if the block timestamp is lower than the end time. Otherwise, we throw the error message auction ended, or the auction has then already concluded. We are after the end time. And then we add a second requirement where we say that the message value must be larger to the highest bit, so the current highest bit. Otherwise we say bit is too small, it's not the highest bit, there is a larger one. If that's the case, if both these requirements are satisfied, then we first set highest bit equal to message value and second highest bidder equal to the message sender. Now, before we can move on, we actually have to make the bit function payable. That's important, of course, because it must be able to accept ether, so payable right here. And then we can add a new section. Let me do that through a comment where I say amount withdrawable of previous bits, and we add a mapping from an address to an unsigned integer, and we call that mapping pending returns. And the idea is that we store the amounts that can be withdrawn in this mapping. Let me quickly fix that typo right here, so small m. All right, and then we can add the pending returns to the bit function. So first we have to check something. So we have an if statement. If the highest bit is unequal 0, then what we're doing is we are setting the pending returns of a specific address of the highest bidder plus equal to the highest bid. So we do a plus equal, not an equal, because we don't want to override whatever has been stored in there before. And then we add another function as the counterpart to what we just did, which is the withdraw function. It's an external one. There is no reason that the contract itself must use it. And we use the returns statement and return an unsigned integer called amount. The first thing we do is actually defining that amount. So amount will be the pending returns of the message sender. So we use the message sender address here. And then we add another condition, another if statement, and say if the amount we've just defined is larger than 0, then do something, otherwise do nothing. And the something we do in case it is larger is we set the pending returns of the message sender equal to 0. So we modify them, we readjust them to 0. And then we use the address of the message sender and make it payable. So payable message sender dot transfer, and we're going to transfer whatever we have specified in amount on the first line of the function body. Now what you can do if you want to do that is optionally, that is write return amount. You don't have to do that because you already defined the return statement in the header of the function. So you don't necessarily have to do it. Let us define another function, and this is the auctionEnd function. Again, it's an external one. No reason why it should be called within the contract. And there are actually 3 parts to it. So first, we check all the conditions. Second, we apply all internal state changes, so a part of this contract. And third, we interact with other addresses. So in this case, we're going to send the highest bid to the beneficiary. So first, the checks. We require that the has ended is set to false, so it cannot be set to true. Obviously, if that would be the case, then the auction would already have ended, and then there is no need to call it again. That's also the error message. And then the second requirement is that the block timestamp is larger equal to end time, so that we know that it actually should be able to end. The auction has reached a time where it can end, and otherwise we say as an error message, wait for auction to end. In the second part, there isn't too much to do. In the second part, we just have one statement that is has ended, so the has ended variable will be sent to true. And then in the third part, what we're doing is we are taking an address, the address of the beneficiary in this case, make it payable, again, dot transfer, and we're going to transfer the highest bid to the beneficiary. So basically the winning bid will be transferred to the beneficiary. Now there is only one more thing left to do. Let me add a section called events, because here we are going to define 2 events for the contract. And the first one is called new bid, and it has an address, an indexed one, and which is called bidder, and unsigned integer, which is called amount. We define that right here, and then the second event will be called auction ended with a capitalized A. It has an address, which is the winner address. There's an unsigned integer, which we again call amount. And these are the 2 events that we can use in the contract. Now, we have to omit them also. Here they're just defined. We omit them as part of the functions, and the first one will be omitted in the bid function. right here. So we say emit new bit, that's the name of the event again, and then we just define what actually will be stored, and in this case it will be message sender and message value that will be stored as part of the event, so for the logs. And the second event will be emitted as part of the auctionEnd function right here. So we say again emit, we refer to the auctionEnded event, and we use the highest bidder and the highest bid as the two values that will be stored as part of the event. The only thing that's left to do is a comment up here. So I'd like to add a warning, a quick warning. I'm going to say that warning, do not use for actual fonts. On mainnet, that is, it's a good exercise for test nets, and it's great to play around with, but you shouldn't use it for actual fonts. Now let us compile the contract. You can see it's a 0.8.9. You can see the compiler is set to that, and now we press on compile. Let's switch to the deployment tab, make sure that we have injected Web3. You can see we have Robston right here. You can see the address and the ETH amount right here. And when you're trying to deploy, you have these two parameters, arguments, beneficiary, and duration minutes, which isn't a big surprise. It's also part of the constructor. That's why it's there. So we're going to set that. Duration minutes we will set to 20 minutes. And the beneficiary, we're just going to copy our address from MetaMask, the one of account 1. Then we click on transact and confirm. And that's the deployment transaction. We're going to quickly check that on Etherscan. Oh, no, it's already confirmed. Great. So you can see it here and here. So no need to check on Etherscan. That was quick. We see the deployed contracts right here. You have all of the functions. I have the beneficiary set as part of the constructor. Also, the end time right here has ended is set to false. Highest bid and highest bidders are set to the default values of 0 respectively. If we try to end the function right now, we will get the warning, of course, because we haven't reached these 20 minutes end time. That's still in the future. The front end already warns us. It would also fail on the blockchain, of course. So what we can do is use the bid function right now. To bid, we have to send some value along. And we're going to send 0.1 ETH. But if we do that in way, it's a 1 followed by 17 zeros. That's what we're going to do right here. So we define that here in the value field. And then you can click on bid to invoke the function. You can see 0.1 has been sent along. You can confirm it. And now let us check on the block explorer on Etherscan once again. There we can jump, and then we have to wait for a while. Oh, and we already got the confirmation. You can see the 0.1 ETH. You can see that the bid has been placed, and you can also see that right here. When you are clicking on highest bid, you will see this 0.1, and highest bidder also has been set to our account 1 who has initiated the bid transaction. Now let us quickly switch to the second account. And with the second account, we're also going to place a bid. It's a different account also right here. And in this case, we're going to bid 0.2 ETH, or with way a 2 followed by 17 zeros. We could also, as I said, switch just the unit from way to Ether and type in 0.2. Then we click on bid. You can see 0.2 as the value. We're going to confirm, and again we're going to go back to our block explorer to check on the transaction. It's going to take a while until we get the confirmation, but eventually the bid will be placed in the contract, and here we have the confirmation. So let's quickly go back, check the getter functions. We have the highest bid right here that has been changed to 0.2, and highest bidder also has been updated. So that's another address. That's the address of account 2. Now, obviously account 1 has placed a bid of 0.1 ETH, and that's still locked up in the contract. So let us try to withdraw that from account 1. It's not the highest bid anymore, but it's locked as an escrow in the contract. So account 1 is going to call the withdraw function and should thereby be able to withdraw these 0.1 ETH. Let's confirm and check if that's the case. So account 1 has initiated the transaction. Let's check on the block explorer once again. It's gonna take a while, as most cases when we're using a global public testnet, and we have to wait for the confirmation. And that's the case right now. We have a success, and you can see right here that there is a transfer as part of the transaction from the contract to our account 1 of 0.1 ETH. You can also see the update right here. It just switched to 4.97. So that worked. The account 1 was able to withdraw the previous highest bid when it has been outbidden. All right, so let's try to end the auction again. That's not going to work. We have to wait a little longer, and let me speed up things significantly. Alright, and with the power of video editing, we made sure that you didn't have to wait for 20 minutes. Now, let's quickly try again. And since these 20 minutes have passed now, we should be able to do that. Let's check on the block explorer once again. And it's going to take a while, as always. And at some point, we hopefully get the confirmation and the auction will conclude. And as you will see, what it means is that we transfer the value to the beneficiary. That's the case right now. Success, and you can see right here, transfer 0.2 ETH from the contract to the beneficiary address, which also happens to be account 1. Let's jump to the block. You can see it has been created at 8:25 a.m. And when we go back quickly to the transactions and click on the from address, so that's the address of our account 1, and look for the deployment transaction, then we can see that this has been 25 minutes ago right here. So unsurprisingly, it actually worked. Unsurprisingly, we have been able to conclude the auction. You can also see that right here, that account 1 actually got these 0.2 ETH. All right, congratulations. Now you have your first smart contract that actually does something useful. You have a proof of concept for an auction contract, and I think that's really exciting. We will build on that, of course, but that's something for a different video. And with that, stay curious. See you soon.